and then into its own block with probability proportional to alpha. So this is if B is already a block, here if B is empty. And so you can see that alpha controls the number of blocks in the partition, right? So in the original derivation of this, from Ewan's, alpha was a mutation rate in genetics. So mutations meant that individuals had different genetics than everyone else in the sample, and that corresponded to opening up a new table or a new block in the partition. So higher values of alpha are higher mutation rates. And the way to prove compatibility from this is just by induction, because for each partition of n plus 1 elements, there's a unique partition of n elements that we project to under restriction. So in order to generate any specific partition, we have to first generate its restriction, and then we have to do the right thing under this conditioning. So if we assume that this partition has the Ewan's distribution, then the probability of the partition after n plus 1 steps will just be the probability of this times this conditional probability. So if this has the Ewan's distribution, then if we insert a new element, so we're always going to get the correct normalizing constant n plus alpha, so that'll go into the rising factorial, and if we add a new element into a new block, then we'll get an extra alpha, so the number of blocks will increase by 1. Otherwise, we'll just affect this factorial factor for the block that we enter. So we easily see that that we get a compatible family of distributions, and we can see that they add up to 1, right? Because these conditional probabilities add up to 1 at every step. Okay, so I'll come back to this a bit at the end. What I want to go to now is the second part, which is on random permutations. So when we were studying partitions, we were interested in how partitions behave under this invariance property of relabeling. So in this case, we're interested in just what the induced integer partition is from the blocks from the block sizes of a partition. Exchangeability for random permutations isn't quite as interesting. I mean, it is interesting, but there's only one exchangeable distribution on permutations, and it's the uniform distribution, because the permutations are a group. And so here we're interested in this statistic, the number of inversions, but the analog to compatibility here is to consider how the distribution behaves under reduction. So I'm sure some of you have come across this in the study of pattern avoiding permutations, right? So the reduction of, so in this case I'm always writing rho as a sequence, or is a string of length n, linear order of the set of n elements. And the reduction of some subsequence, so if I take any subsequence of length m, so m is less than n, so I take then I define the reduction to be the unique so it's the unique order isomorphic ranking of the set of size m. Okay. So for example, if I take the odd labeled subsequence of this ranking here, what I get is the reduction of this string, which corresponds to, which is order isomorphic to 3, 2, 1, 4. Right? Okay. And so now what I'm going to be interested in is the property of what's called spreadability, which means that the distribution, so again what I can do is I can generate a random ranking of a set of size n, and then I can look at any subsequence of length m, and I can take its reduction and I get a random ranking of the set of size m, and I want that induced distribution to correspond with the marginal distribution that I originally assumed. So again, I say a family of random rankings is called spreadable if the probability of the reduction. So now I'm writing superscripts instead of subscripts because well, maybe I can write it this way to be consistent. So if I take any consecutive subsequence, so I'm defining a special case of this, and because the Mallows distribution doesn't satisfy the more general case. The probability that the reduction of a consecutive subsequence of length m, so indices I up through I plus m minus 1, corresponds to some ranking of length of the set of size m is equal to the distribution for the ranking of index by m. Okay, and so you could consider an extension, a generalization of this where we allow for subsequences, arbitrary subsequences, and we want this property to hold. But that's a much stronger property that doesn't quite hold for the Mallows distribution.
Does it exist in distribution?
Well, the uniform distribution.
Yeah, but exact.
And I don't know one off the top of my head. I would think there does, but I can't quite think of it. Okay. So now if we look at the Mallows distribution up there, so this is the distribution that. So if q is equal to 1, we get the uniform distribution, because q is just 1, and we get the n factorial. If q is less than 1, then we are favoring rankings with fewer inversions, and if q is greater than 1, then we favor inversions. And so if we take Rn to be from this distribution for each n, then the family satisfies the spreadability property. Okay. And I won't go through a complete proof. I'll just give an illustration that is probably not satisfactory, but it'll just show. If anything, it should make this definition more apparent if it's not clear. So if we consider the case n is equal to 3, and what I'll do is I'll write the probability, but I'll multiply out the normalizing constant just to make it easier to read. So if I consider all of the permutations of 3 elements, then the distribution is just q raised to the power of the number of inversions, right? So here we have q to the 0. There's 1 inversion here. There are 2 inversions. This has 1. This has 2, and this has 3. And so what we want is, if we sum up the probabilities that correspond to some, that for some specific subsequence correspond to the reduction of a specific ranking, then we want that to correspond to the Mallows distribution on a set of that size. And so in this case, so these first three, well, if we just consider, for example, the ranking induced by the first two elements. So these first three rankings will induce the ranking 1, 2, with no inversions. And so if we add these probabilities up, then we get 1 plus q squared. So that's adding these. The denominator is the same in every case. And so we get cancellation here. This is equal to 1 over 1 plus q, which is equal to the probability that a ranking of size 2 is this, because there's no inversions. And the same would be true if we did it down here. And if you do it for arbitrary, it doesn't have to be on the tail. It could be in the middle if we had a longer ranking. And the reason this is true is because there's an analogous, so the proof would follow from an analogous construction to this Chinese restaurant construction. There's a way to sequentially construct a random distribution, a family of random rankings from the Mallows distribution. And the way it works is, think about, so let me just quickly mention this. Suppose at time n we have say this ranking. Then what we can do is we can insert the new element in any one of these places. And the new element is 7, so it's larger than every one of the existing elements. So wherever we put it, we'll introduce that many inversions, right? So here we introduce 0 inversions. Here we introduce 1, 2, and up to here we introduce 6 inversions. And so if we add these up, we get the denominator that we would get in the rising factorial. And so we can build this up sequentially in the same way. So these are easy to simulate on a computer as well. Okay, so in the final few minutes here, I'll talk about what I see as potential to study problems involving pattern avoidance for these random objects. So in an enumerative context, we're interested in enumerating, for example, the number of permutations that avoid a given pattern. Right? I know there's several people in this room interested in that. And so that corresponds to exactly to calculating the probability that a uniform random permutation avoids the pattern, right? Just up to the constant, the normalizing constant n factorial. And so I think we could ask the same questions for these distributions, which are of interest in various applications for various reasons. I'm sure the questions are just as difficult, or if not more difficult there than they are in the regular enumerative setting. But for example, if I consider the restricted growth function of a partition, so I know that many people here have talked about or worked on permutation patterns, so I'll just talk about partition patterns for a minute. So we say that a partition pi avoids some pattern, say tau. So tau is going to be the restricted growth function of some partition of length m. And we say that a partition pi avoids it if its restricted growth function avoids it in the sense that there does not exist a subsequence such that the reduction, and now I'm talking about the reduction of the restricted growth function, but the definition is the same, is equal to tau. Okay, and so as an illustration, take our running example which has restricted growth function here. So this avoids, for example, the pattern 1, 2, 3, 3, but it does not avoid 1, 2, 3, because we have a subsequence. And so I think it would be interesting to consider what's the probability, for example, that a random partition, say, avoids a given pattern. So as a very simple illustration, one of the only ones that I can actually do as a trivial calculation to compute, well, what's the probability that a random Ewens partition avoids, say, this partition, this pattern 1, 2, 2. Okay. So in this case, in order for a partition to avoid this pattern, what has to happen? Well, we always get a 1 at the front of the restricted growth function because of our convention that we always list the blocks in increasing order. So element 1 is always in the first block. And so the only way to avoid this pattern is if all of the blocks beyond the first block are singletons. Okay? And so now we have to sum the Ewens probabilities over the set of all partitions that avoid this pattern. And so we can sum here over any number of blocks. So the number of blocks will be from 1 to n. We have alpha to the number of blocks over the normalizing constant. And now we have the combinatorial factor associated to each of the blocks. Well, if the partition has k blocks, then it's all of the blocks beyond the first, there's k minus 1 of them, they have to be a singleton, so all the other elements have to be in the first block. So there's n minus k plus 1 elements in the first block, so we get the factor n minus k factorial. And then we have to count how many such partitions are there. Well, with the first element 1 is always in the first block, and so there's n minus 1 elements to choose from, and to choose k minus 1 singletons from. And so we have n minus 1. Choose k minus 1. And so this, we can get an explicit formula. And of course, asymptotically, we get a nice expression as well in this special case. But in general, this is hard to do, but I think that there's potential to use some of the techniques that people here would know more about, and also to use computers and simulation to maybe answer some of these questions. So I'd be interested to hear anybody's thoughts on that. So I think I'll stop and take questions.